So, hello Year 12 and welcome to a video that is just designed to go through the mark scheme for the work that I set you last Friday, which was your lesson work, to have a look at the 2018 AS paper 1, in particular questions 3 to 6. And I chose these because I think they highlight just how well you need to know the experiments and the practicals that you do, and possibly it might highlight some details that you thought were unimportant, which actually the mark scheme does demand that you know. So, moving swiftly on to question 3, sulfuric acid and potassium hydroxide, neutralization. This is titration based on CPAC 3 here. Titration carried out with the following method. Potassium hydroxide solution was placed in the burette. The initial reading was recorded. Sulfuric acid was put in a conical flask. 3 drops of phenolphthalein indicator were added to the sulfuric acid. Potassium hydroxide was added from the burette until the solution just changed colour. Burette reading was recorded. Repeat titrations were carried out until concordant titers were obtained. What would be the most appropriate apparatus to measure the 25 centimetres cubed of sulfuric acid? Hopefully you would all have gone with the pipette. What is the colour of the solution when neutralization has just occurred? So you're adding the phenolphthalein to the sulfuric acid, so it would start colourless, and as it gets alkaline it would go through to pink. So at the end point, when neutralization had just occurred, it would be pale pink, and this is what we see here. And you can see the reasons why the other options are wrong. Here are your results. So you've got to fill in the table here with the initial reading, the final reading, and the titration volume. Well, the initial reading 4.1, 2, 3, 4, 5, 6. So 4.60. Don't forget to record it to 2 decimal places, and at the end 32.1235, so 32.35 there, and you can work out what the difference in volume is there, again recording it to a 0 or 5 at the end. The best, well, I suppose we'd better do this, hadn't we? So 32.35 minus 4.6 is 27.75, okay? 27.75. Okay, looking at these, it's clear that that's not concordant. These two are concordant, that one is not. So even without knowing whether 0.1 or 0.2 is the correct precision here, the correct value of error, we can see that these two should be averaged to give the value of 27.00. So here we go, 32.35, 4.60, 2 correct readings to the nearest 0.05, correct subtraction of the two values to 2 decimal places. Don't forget that. Calculate the concentration moles per dm cubed of the potassium hydroxide solution, giving your answer to an appropriate number of significant figures. You should be able to do this, but I just flagged the appropriate number of significant figures here, which is really important. So you calculate the moles of sulfuric acid from the concentration times by the volume that was put into the conical flask, 0.002. It's a 2 to 1 ratio, of course it is, H2SO4 to KOH, 2 to 1 ratio, so there's 1 mark for realising that you need twice the volume of hydroxide. And finally, concentration is moles over volume. Remember, of course, to put the volume into decimeters cubed gives you this on your calculator, which you would round to, and it says an appropriate number, that's 2 or 3 significant figures, 0.148, 0.15 mole per dm cubed. This was difficult. You might have been a bit worried about some parts of this, but actually you do know all of the stuff that you need to know to answer this question. An ionic compound contains a metal cation and a non-metal anion in a 1-to-1 ratio and water of crystallization. The compound can be represented Mn.xH2O, where X is the number of moles of water of crystallization per mole of Mn. A sample of Mn.xH2O was dissolved in distilled water to produce a colourless solution with a concentration of about 0.5 mole per dm cubed. 2 centimetre cubed of the resulting solution was transferred to 2 test tubes and some tests were carried out. Right, we've added barium chloride. And barium chloride, you should know from GCSE, is used to test for sulfates. So one of the anions, name or formula, is the sulfate. If you are going for the actual formula, you must get it right, SO4 2-. Now, why do we acidify this? And that's because actually there are other anions that will give you a precipitate with barium chloride. And the one we went through in lessons was that the carbonate anion, CO3 2-, would also give you a white precipitate. Okay, and this is why we need to acidify it to remove this one. Addition of 1 centimetre cubed of dilute hydrochloric acid to the test tube resulted in no further change. Give the formula of the anion. Right, that means it must be the sulfate, because if you added the carbonate to acid, it would fizz and release carbon dioxide. So this is why we acidify it, so that any carbonate will fizz, release CO2 and dissolve. So there you go, you can see sulfate SO4 2-, carbonate CO3 2-. You could have had sulfite, not one I would have expected. What it says under here is penalise lack of charge. So if you gave the SO4 or CO3 and you got the charge wrong, then you couldn't have had it. Here it does specifically say you must give the formula. Only penalise lack of charge if not penalised in force. So if you wrote sulfate and then you wrote SO4-, you would have lost this mark. But if you wrote SO4 2- in both, or SO4- in both, you would have got that one. What is the charge on the cation? Okay, cations, remember, are positive. Cats purr, I can't do that. Cats are positive, cations. If it's 1-to-1 ratio, and we know that the anion is SO4 2-, the cation must be 2+ C. A flame test gave no change in the flame colour. Give a possible identity of the cation M. This is why you need to know your flame test colours for groups 1 and 2. That expanded range that you need to know. The ones that give no flame colour are magnesium and beryllium. Magnesium would be the obvious one. People always get confused. It doesn't give a bright white flame according to the exam board. You might be remembering the oxidation of magnesium, the fact you have to wear filters or use filters to look at it. But actually, the flame test for magnesium does not give a colour. Most of the output of the light is in the ultraviolet region of the spectrum. So it would have expected magnesium, cation is Mg2+, or the magnesium ion. Do not award use of the symbol or just Mg as I just did. It wants the cation, so it wants Mg2+. Heating the hydrated compound results in the formation of the anhydrous ionic solid Mn by the following reaction. Heating a sample of the hydrated compound reduced the mass to 48.9% of its original value. What is the formula of X? Right, well, the first thing we need to know is that Mn is MgSO4, and the mass of that, magnesium sulfate, 24 plus 32 plus 64 is 120 grams per mole. Okay, so now what we could say is we know that 100 grams of this would give us 48.9 grams of magnesium sulfate, and therefore it would give us 51.1 grams of water. So we can do some mole calculations. 48.9 grams divided by 120 gives us 0.4075 moles of MgSO4, and 51.1 divided by 18, the formula mass of water, gives us 2.839 moles of the water. And if we divide both by this, that gives us a 1 to... So that is 6.97. Let's call it 7. It's a 1 to 7 ratio. Okay, so it was actually, for 4 marks, not too difficult. So you can see here, calculate the relative formula mass of magnesium sulfate for 1 mark, working out the number of moles of each is your 2nd mark, divide ratio by the smallest to get a 1 to 7 ratio. That is the 3rd mark, and the 4th mark is for just saying that x equals 7. Question 5. A student made crystals of a metal chloride, they're liking these ones, aren't they, JCl2.6H2O, by reacting the metal carbonate with hydrochloric acid. The product was purified. Okay, this is basically like your GCSE required practical. So look for the similarity here. We've got a set amount of acid, 150 centimetre cubed of hydrochloric acid, concentration 0.8 mole per dm cubed, transferred to a conical flask. Flask was warmed gently using a Bunsen burner. Spatula measure of metal carbonate was added to the acid. When the reaction was finished, more metal carbonate was added until the metal carbonate was in excess. So this is your required practical where you are making a salt. The resulting mixture, from GCSE, the resulting mixture was filtered into an evaporating basin. The evaporating basin was heated using a Bunsen burner to concentrate the solution. The concentrated solution was allowed to cool and crystallise. Once crystal formation was complete, the resulting mixture was filtered for a 2nd time. The resulting white crystals were rinsed with a small volume of ice cold water. So this is the new bit. This is the A-level addition to the practical, which is we are getting pure crystals here by rinsing the crystals with a small volume of ice cold water. Describe 2 observations that the student might make which show that the reaction in step 1 has finished. Okay, you're adding a carbonate, so it's going to fizz. So stops fizzing would be the first one, because as you're adding the carbonate, it will react with the acid to fizz. And the second thing is you will see that the solid will start to accumulate at the bottom. So solid at bottom of flask. Now there may be a better way to describe that. Let's see what the mark scheme says. Description making reference to the following points. The fizzing or the effervescence stops, we got that. The metal carbonate or the solid disappears, or allow metal carbonate solid dissolved, or just a clear solution. Okay, right, so I misunderstood the question there. So what it's asking is, how do you know that you should add more metal carbonate rather than how do you know when it's in excess? And the answer that they were looking for is that all of the solid would disappear, not dissolve. It's not dissolving, it's reacting, but it disappears, and that's when you would add more of the metal carbonate. So I misread that. What's the purpose of the filtration in step 3? Well, just like in your GCSE, it is to remove the excess metal carbonate. Why are you using a small volume of ice cold water in step 6? Well, you're using the ice cold water to prevent the crystals from dissolving. But the question might be, well, why are you rinsing it at all? Why are you adding the water? And that's what the 2nd mark is for, and that is to wash off any impurities. So wash off soluble impurities. Remember, if it's a 2-mark question, we're looking for 2 distinct points. So here we go. So as little product as possible dissolves, but why are we adding water in the first place? To remove soluble impurities. Ignore, rinse, wash the crystals, clean the crystals, because that's not specific enough. The student obtained a mass of 14.26 grams of hydrated crystals. Assuming that the percentage yield is 100%, use the information in the procedure to give the possible identity of J. So if we go back a couple of steps, we've got hydrochloric acid reacting to form the metal chloride JCl2.6H2O. So HCl plus JCO3 going to JCl2.6H2O. 2HCl, yeah, plus H2O plus carbon dioxide there. I think that's right. And obviously we need some more waters in here. 2HCl, JCl2, H2O, CO2, and yeah, we need 5H2O as well, adding into that. Right, now you might be tempted to work from the mass of JCO3 that we started with. Let me just check, it was JCO3, it is. But unfortunately, we are told that we're adding an unspecified amount of the carbonate, so we can't work from that. But what we do know exactly, and the reagent that was limiting, was the acid. 150 centimetres cubed of hydrochloric acid at a concentration of 0.8 moles per dm cubed. So what we do know is the moles of acid that we used in this. So of the HCl, it was 150 centimetres cubed times by 0.8 molar. So divide that by 1,000 and we can work out the number of moles of HCl. 0.15 times 0.8, which is 0.12 moles. Now we therefore know that will give us half the number of moles, because it's a 2-to-1 ratio of this, so that should give us 0.06 moles of this. We've got the mass of the hydrated crystals, so MR equals mass over moles, so 14.26 grams over 0.06 moles tells us that the MR is 238. So that's the MR of the whole thing. So from which we can subtract 2 lots of chlorine, which is 71, and we can subtract 6 lots of water to get minus 71 minus 6 times 18 gives us a mass of about 59 for J. Now remember, this must be a 2+ ion, so we're looking down there, and hopefully the closest one is barium in group 2. Let's see if I made a mistake here. So 59 nickel. If you worked out that the proper to 3 significant figures was 58.7, which I do actually have on my calculator, then you would have worked out it was nickel. So again, I would have made some mistakes here by presuming that it had to be a group 2 metal. It didn't, it could have been a transition metal. The student was surprised by the white colour of the crystals in JCl2.6H2O in step 6. This did not agree with the possible identity for J for the calculation of B. Why was the student surprised? And this is because transition metals form coloured compounds usually. So that's what you'd expect. Transition metals would form coloured compounds. It's the group 1 and 2 metals, the so-called S-block metals, that form white compounds. So the white crystals would be more likely to suggest that that it was a group 1 or group 2 rather than a transition metal. So what does it want? It wants, for the first mark, crystals are white, suggesting an S block or group 2 element. And the second mark, the flame test, would be used to identify what the cation or the metal ion actually was, and I didn't put that in there. The flame test colour was crimson red. Identify J. Right. So it's not calcium, because that is orange red. It's not barium, because that is green. We know it's 2+, so it can't be lithium. That's often described as scarlet red, so therefore it must be strontium. Okay, so there you go. The only correct answer is D. Calculate the actual percentage yield of the reaction, which produced 14.26 grams of crystals. Give your answer to two significant figures. Okay, here's the mark scheme for that. You calculate the molar mass of strontium chloride. You know that 0.06 moles, we've got that previously, 0.06 moles of that times by the relative formula mass should have given you 15.996 grams or 16 grams. 14.26, which was the actual yield, over 15.996 gives you a yield of 89.147%. Okay, so first mark was for calculating the relative formula mass of that, 266.6 266.6, and then the percentage yield for the second mark. Only 2 marks there, not too difficult. Finally, chlorine and iodine in the same group in the periodic table. Complete the electronic configuration of chlorine using the SPD notation. So as we look up on the periodic table, we can see that chlorine is 1s2, 2s2, 2p6. That's taken us up to neon. 3s2. That's taken us up to magnesium. 3p5. There you go. So that's all fine. For 3p5, oh, if you really want to go crazy, you could split it into the px, py and pz, but no need to do that. Explain why iodine and chlorine have many similar chemical reactions. Well, this is just GCSE, isn't it? Same number of valence electrons. So valence or outer electrons. So loses gains same number to fill shell. Something like that. It's 2 marks. We need 2 separate points. Let's see what it was. Iodine also has 7 electrons in the outer shell, so the electronic configuration, the number of electrons in the outer shell, govern their chemical reactions. Possibly would have got 2 marks for that. Not quite sure there. And now, same number of electrons in the outer shell, valence electrons for the mark 1. What I haven't really said was that the number of electrons governs the chemical reactions, but I have said gains the same number, so I'm not sure whether that would have got a mark in reality. Oxidation numbers of sulfur in the 3 sulfur containing ions. Well, oxygen is always 2- unless bonded to fluorine or another oxygen. So therefore the O3 gives us 6-, but we've got the 2- there, so the sulfurs must be 4+, so the oxidation number must be 2+. Here we've got 4 oxygens, 8 minus, but we've got the 2 minus there, so that must be 6 plus. And here we've got the 6 oxygens, so that's 12 minus, but we've got the 2 minus there, so the 4 sulfurs must be 10 plus, so therefore each one must be 2.5 plus. And checking those, there we go, plus 2, plus 6, plus 2.5. The equation for the reaction of iodine with thiosulfate ions is this. State in terms of electrons why iodine is classified as an oxidizing agent in this reaction. It's an oxidizing agent because it is reduced. An oxidizing agent is itself reduced, and that means it gains electrons. It takes them from something else, which it oxidizes. Therefore, it's a gain of electrons by iodine. Use your answer to B1 to show that chlorine is a stronger oxidizing agent than iodine. Well, if we go back here, we can see iodine gives S4O62 minus. Chlorine just gives SO4. So we're oxidizing up in both cases, we're oxidizing up the thiosulfate from 2 plus. So iodine is going from 2 to 2.5 plus, but chlorine is going from 2 all the way up to 6. So it is sulfur in higher oxidation state. It has lost more electrons. Okay, something like that. An answer that makes reference to chlorine oxidizes sulfur from plus 2 to plus 6, whereas iodine only oxidizes sulfur from plus 2 to plus 2.5. Yeah. Write the ionic half equation for the reaction of aqueous S2O32 minus to give SO42 minus. State symbols not required. Lots of students really struggle with this kind of thing. So S2O32 minus going to SO42 minus. Okay, first thing to notice, 2 sulfurs there, so we must end up with 2 sulfates. On the right hand side, we've now got 8 oxygens, so we've got 3 from here, so we must have 5 waters. Remember, if we need to balance oxygens in this type of equation, we balance it with waters. If we've got 5 waters on the left, so 5, 6, 7, 8, giving us 8 there, then we've got 10 protons that must do something, so they must be released, 10H plus being released on this side, and we just need to now make sure that the charge is balanced. So on the left hand side we've got just a charge of 2 minus. Here we've got 4 minus and 10 plus, so that is currently a 6 plus, so we also need to balance that by adding 8 electrons. So just check that one more time. 2 minus over here. We've got 4 minus plus 8 minus, which is 12 minus plus 10 yeah. So that looks good. Let's just check that's right. This is being oxidized here. Oxidation is loss of electrons. The electrons are on the correct side. Just having a look. Yeah, so S2O32 minus 5H2O, 2 of those, 10 and 8. Yeah, we got that all right. Just follow the procedure. Oxygens get balanced by waters, then you balance any hydrogens with protons, and finally balance the charges using electrons. Use your answer to above and the half equation for chlorine to write the overall ionic equation for the reaction. Well, the chlorine just accepts 2 electrons, as we can see here. So we need to multiply that by 4. So the other equation is that 4Cl2 plus 8 electrons go on to form 8Cl minus. and therefore when we add those two equations together, 5H2O plus S2O3 minus plus 4Cl2 plus 8 electrons going to 2SO4 minus plus 8Cl minus plus 10H plus 8 electrons. Cancel out the electrons which balance, and we should have the correct equation, which we've got up there, yeah. So 4Cl2, one of those, 5 of those, 8 to 10. Yeah, absolutely. There we go. I hope that was useful. I'll talk to you in a couple of weeks when we get on to topic 8, Hess cycles. Other than that, enjoy the weather. I hope you're surviving all right at home and that you're all healthy. And see you in 2 weeks.